name is Arslan, and I'm a SWE SRE at Google. SWE means software engineer, and SRE is site reliability engineering. It's a dual role. So, yeah, and I'm based in the Zurich office in Switzerland, but I'm from Pakistan. Let me give a brief introduction to myself. I don't have a slide to introduce myself, but I can speak briefly about it. So I'm born in Pakistan. I studied until my A-levels here in Lahore, and then I moved to Hong Kong to get a bachelor's degree. I lived in Hong Kong for around 6-ish years. I studied there, worked there in many different industries. I think for the first 2 years of my career, I was just hopping around 8 months, 6 months in a company, and then moved to the next company. It was very random. Worked in fintech, crypto, startups, like tried all possibilities really, and then eventually realized that I like distributed systems, I like core engineering, so then I joined this team in Google. So the title of today's talk is, it's all about scale, and the goal is to discuss the design and reliability at planet scale. And this topic is very close to my heart because that's what I do 8 hours every day at Google. My team is Borg team, and this is basically like a core system in Google that runs everything else. So now you use YouTube, you use Maps, you use Docs, you use any other Google product, it runs on that core system. So reliability and scale becomes a very important factor in that system. So that's what I do, and hopefully in today's talk, you'll get to learn some new things that we learn in Google. So yeah, first of all, the agenda. I'll briefly introduce the term SRE, Site Reliability Engineering, because I don't think I've met a lot of site reliability engineers here in Pakistan. It's a role that is normally required when for companies that work at high scale and high reliability requirements. So, and then we'll talk about some of the architectural principles that at least I learned, and I want to share them with you as well. And then building on to that, we'll talk about some ways in which we handle faults in large, scalable, and reliable systems. Okay, yes. So inside reliability engineers, who are we? We're basically software engineers, but we have a very targeted mission towards thinking about reliability and scalability. And we try to keep systems running, really. And it sounds really simple, like software ko chalane mein kya mehnat lagti hai, but it actually turns out to be very complicated when you are running around on like 5 million servers for 2 billion users. This becomes quite a challenge. And our goal is to, as Google is scaling up, as our partners are scaling up, we need to scale up as well and become more and more reliable. Fun fact, people use google.com to check the internet connection. So if Google is down, people think the internet connection is down. So that's the bar that we have to meet, right? We have to be always available, always be available. How do we do it? There are some proactive decisions we make in our architectural design, and also some reactive measures in case things go wrong. Why we do it is, yeah, our customers require that. Our users like you, sitting on their phone, you always expect user maps to work, or Google Maps to work. You expect Google Search to work. You expect YouTube to work all the time, right? So those are the expectations that we need to meet. Okay, so first of all, to learn about how to design scalable systems, we will try building one, right? So the easiest way is that to try to build one, and let's take an example of a photo hosting service, something like Google Photos that you use. So there are 4 major requirements that we're going to take care of as we're building this system. And as we build this system, I'll highlight some of the principles that we use and a sneak peek of how we build systems at Google. Okay, so users should be able to upload their photos. Users should be able to search their photos, as they should have like a UI to search, and everything is public. So that means that we'll have a lot more read requests than write requests, or a few folks will upload the photos, but everyone can view it. So that means we have a high read request workload, and then we want to make sure that the service is globally available throughout the globe. We have users in Asia, Europe, and America, so we want to make sure we're all available for that. Okay, so first of all, okay, Yeah, so let's start very simple, right? I'm not going to focus on how the code is written or how which language is used, which framework is used. That's irrelevant to this talk. Let's imagine the code is written and now we have to just run it, right? Okay, so we put it in the machine. It has a processor, it has a RAM, it has an SSD or a hard drive attached to it, and then we run it. So, well, everything is fine, right? Job done. Do we need to do anything else? The service works, it's up and running. I wish it was that simple. I would have just ended the presentation here. I wouldn't need to take it further, but it's not that simple, right? So the first principle that is super important is to aim for a stateless service. So aim for a stateless service, right? So we move the application logic away in a separate system, and the storage system is separate, because the failure modes of these two things are very separate. Compute systems have a very different failure modes. They fail in very different ways as compared to a storage system. Like in compute systems, we have these, like a noisy neighbor problem. We can have CPU overload if there's not good isolation between different workloads. A storage system, they fail due to, well, one is disk corruption or data corruption. There is also like a risk of like disk full, the storage ran out of free space. So there are different failure modes. So you want to isolate these two, separate them out, have like a stateless service. There are a lot of other benefits of having a stateless service, and and we will see how, these benefits as we try to scale up the service. So moving on, but this is still not enough, right? We just separated the two functionalities. We have limited compute. We only have one machine, so we can only accommodate a few users. Then we also have poor reliability. It's just one machine. And if that one machine goes down, due to whatever reason, the service is unavailable, right? And it's not even unexpected failures. Unexpected failures can happen all the time, hardware, software, and that's what we need to learn to acknowledge, that this will happen. It may happen less frequently or more frequently, but it will happen. And even if the unexpected failures don't happen frequently, we have these software upgrades, right? You need to update the OS, you need to update the application logic, and whenever you update, you have this one single server, the service will go down. So that's not reliable enough. What do? You try to solve the scalability and reliability problem with one solution, and that's horizontal scaling. So the two major concepts of scaling, horizontal scaling and vertical scaling. Now, vertical scaling means you have a bigger server. You get a chunkier machine with more CPUs, more RAM, terabytes of RAM, and then you have this large CPU that can handle a lot of workload. It can handle a lot more requests. But then on the other hand, you have this horizontal scaling, which means that you have smaller machines, running on smaller CPUs, less RAM, but you have many of them. So horizontal scaling is generally more expensive, but it comes with its own benefit of reliability. The reliability means that if we have a smaller failure domain. Our failure domain is like a term that we use in this industry quite a lot. Basically, this means that what are the group of services or systems that are impacted if one thing fails. So if in this machine, if one thing fails, only one instance of the service will be affected. We have many instances, right? In that case, we have one machine again. If that fails, everything goes down. So we need to adopt horizontal scaling. We can scale up. We can handle more users. We can handle more requests. Okay? And then we also get the benefit of reliability, as I mentioned. So now we're introducing another component. Since we have many machines here, we still have one storage for now. We have many machines running the same stateless application logic. We need to add a load balancer. Now, a load balancer is another service that generally shares the load or shards the request in multiple machines. So that's an important component that we need as we scale up. Okay, so, well, this is still not enough, apparently. Most of the people stop there, but I guess when you go for really global availability, high scale, you need to think further. And one thing gets very important is if your application logic is doing too many things at once. So if you look at it, all the code lives in that. If I go back, all the code lives in that one instance. Uploading, searching, serving the images, all is there. All of them is there. And these are very different operations. So if you look closely, we have this image uploading operation is very different than image hosting operation. Image uploading will be definitely a lot less QPS. QPS means queries per second. That's, I think, generally people use the requests are also much longer. They can last several seconds. Payload is very variable depending on how the photo was taken. If it's taken on a mobile phone or a DSLR, really the size really varies. So so the request, the payload of the request will vary a lot. On the other hand, serving operation is completely different again. So we have this mix of requests coming to the same machine. Definitely something we can optimize. One little tip is, again, if you're uploading a photo, we sometimes do some basic image processing to create a thumbnail or to resize the image so that it takes less space. This kind of operations can be done better on a different hardware, like a GPU, whereas serving operations might be better on a CPU, right? So ideally, we should split these two things apart, run them separately, and eventually and run them on very optimized machines. So this is a more of a throughput optimized workload. This is more of a latency optimized workload. Here, latency matters a lot. Upload karte waqt, users are not that concerned that it's slow. When searching through the photos or when viewing the photos, the latency is really important, right? So you split them apart. You keep the replication. You horizontally scale both the things, right? And you can optimize for the hardware further. Again, so that's for the next iteration. Is this enough? Or do we need to do more? Can anybody tell me what's wrong with this, or what more should we do? Yes. Exactly. And this whole process is exactly how we build systems in Google as well. We start with something very simple, and we build, okay, this is wrong, and then you build onto it to add more solutions. And that point is so true. We have two single points of failure. If that's one storage instance fails, we're done. The whole service is done. All the replication doesn't matter. And similarly, load balancer, that's the entry point for every request. If that fails, the whole stack becomes unavailable, right? So what do we do? Well, an easy solution is replicate everything. Yeah, load balancers, you will need to have multiple instances of that. Storage, you need to have multiple instances of that. And there are many different ways how you shard them, and you need to shard them in different locations as well. We need to have, again, as I said, the service needs to be globally available. So if a particular region goes down, for example, there's this massive power outage in Lahore, and all our stack is in Lahore. All the users across the globe will be affected, right? So you wanna spread the risk geographically as well. You'll have your services running in Lahore, then somewhere in Europe, then you'll have in Asia, Americas, all over the place, right? So these different instances can go in different locations, and that's exactly what we do. So for reliability, replication, redundancy are two very important concepts. Now, I've been talking about mostly the stateless services, right? So, but now I think I want to talk about what happens in some cases you need to manage state. It's generally harder to build stateless services. Although it's good, it has its benefits, but sometimes you just can't avoid it, right? Sometimes you need to have redundancy and you need to manage state. So that's where things get more tricky. And we have two major concepts that are very important to do that. First of all is cap theorem. How many of you have heard of cap theorem here? Of course, yeah. Okay, very few people. Okay, so this is a cap theorem states that if you have any system that allows for partitioning, allows for sharding or partitioning, you can only achieve from consistency or availability. You can't do both. Like if you have a system that has partition tolerance, generally, mostly this is used for storage systems, very common, but it can be used for other compute systems as well that share a particular state. You can only do, basically the goal is you can only pick two of them. You can't pick three. It's like a hard, you can say a physics universal limit. You can find your ways around it, yes, but truly you can only pick two of them. So this is where, but then you ask, we have, how does companies like Google, who want very high consistency of data, very high availability, and you want to have partition tolerance, how they do it? We actually build different systems they're optimized for different needs. We have systems that are optimized for availability, and we try to assume that the data will be inconsistent, so we add extra checks for that. But the whole storage system has the risk of inconsistency. But there are other systems that are, I don't think it's my fault, I don't know. But there are other systems that are optimized for consistency, but they face low availability. So so that's what you need to pick. And as a designer, of a distributed system, you need to pick your battle, right? Okay, this is what I'm going to optimize for, and this is something I'll have to let go. Everything can't be achieved. So don't try to achieve anything. Even at Google, we don't try to do everything. We don't try to optimize for everything. That's just too hard. Okay, so then the next important, and this is actually what I use in my team as well. We have distributed consensus algorithms, and this is where you might have heard about this leader elected processes. So you have 5 processes that want to do one thing, and only one of them can do it. And you have, for example, one of them has the state or the right context to do it. So all 5 of them can't do. Otherwise, it's a waste of compute. Same thing can't be done by five different processes. So you do replicate. You have 5 different processes, but only one of them has to do it. How do you pick which one should do it, right? And how do you handle if that one process fails, the other one takes up the responsibility, or the other one becomes the leader, we say. So that's where these algorithms come in. They try to pick. You have a group of processes that eventually does some sort of very similar to what we call it an election, and they pick a leader, and that leader will perform the action. The leader will have full context or full rights to perform that action. And when the leader is not available due to any reason, the torch or the responsibility will be passed into another process. So this works really well if only one process can have the state. So these are the 2 alternatives. We use it for leader election. Yeah, and then another option is to all the globally consistent DBs that you see, Spanner. I think AWS also has one. I don't remember the name, but they eventually use these consensus algorithms to figure out, okay, which process should make the call. Definitely something very important when you're managing state. Okay, now as I was saying, that in this little exercise, we iterated on the design, right? We started with something very simple, and then we continued. We identified the problems. We continued to build something more complicated, and that's exactly again what we do. I want to focus on this iteration process. That's very critical, and every time you need to ask these questions. Okay, if I'm scaling my application horizontally, then all the components in the application are horizontally scalable as well or not. All the code that you write, or all the dependencies that you have, do they also scale horizontally as well or not, right? Another important question. Then you need to work on the requirements. Okay, for example, we decided that the upload operation will be much better on a GPU. So you need to optimize for that as well. And these are the questions that you can ask. Okay, can I optimize for the hardware and networking for this particular operation? Again, continue to look for ways to improve. As I asked the question, and somebody answered that somebody identified the single point of failure, right? And this is a question we should ask and continue to improve. What we do is we actually do a very extensive monitoring setup. Like we try to make sure how our applications are used and how Google Photos or Gmail, how they are used. We get proper data on like how much compute is used, how much RAM is used, which locations use more, and what are the peak times. When do they have when do the users go down, or when do users upload more photos, so we can scale up accordingly. So you need all this data and have a feedback loop that helps you iterate on the design. Like all the designs that Gmail, more than a decade, I think decade old, we continue to iterate on that design, right? We learn from the users, user pattern changes, user behavior changes, and we iterate on not only on the code side, but also on the architecture, on how it's running side. So that's super important. No. Yeah, okay. So preparation for launch day. Now this is generally a problem for like large scale companies again. When you're launching a product, you expect like, okay, we'll have 1K users or this amount of users signing up on the first day. Now how do you plan for that? How many compute instances I would need to handle 1K users? How would you do that? Any suggestions? No. So that's where you can use either you can use some testing, or there are some, with some basic math, you can try to predict how much usage can you expect. I mean, as you scale up, you have these auto-scaling systems, and you can add more instances, and you can add more compute into the system as new users come in. But for the first launch, and that's really very critical because you don't want your system to be unavailable on the first day of the launch, right? So you want to make sure you get the number right, and you don't want to allocate too much because that'll be too expensive. So let's assume a scenario. We have 1K uploads per second. We can expect 1K uploads per second. We can expect 10K views per second, and then we have 10K thumbnail views, and then we have like 100 per second photo views. So how would you know how much networking I need? How much networking bandwidth I need? With just pure basic math, one image is around 4 MB, right, when you upload, and one thumbnail can be 200 KB. And with simple multiplication, you can say, okay, for the upload server, I need 4 gigabytes per second network speed, and for the serving server, I need 2.4 gigabytes per second. Although the serving requests are a lot bigger, but then we have less data going through, right? We're getting a lot more requests, but overall the data throughput is much less, so we can have a slower networking stack there. Then how many compute instances do we need? How many, when you're horizontally scaling, how many servers should we provision? That again comes up like with some basic testing or some math on how much time does it take to upload to write a photo in the hard drive or to process the photo. We can assume around 30 milliseconds per request, and our server are capable or have enough RAM or concurrency to handle 10 requests concurrently. With that, you can see, okay, we need around 30 instances to start with. So again, this is something that I think you need to do as for the first launch to make sure you launch successfully. You don't provision too much, or you don't provision less. Now, I want to quickly go through some of the that was most of the like pathways we use or things we consider as we're designing a new system. And of course, as those are very generic, but if you go further into building more specific systems for particular niches, you need to consider their own constraints. Fault handling. These are again things that generally go wrong, and I've seen it go wrong, and it will go wrong with your systems as well at some point in time, so better keep that in mind. First of all, as I said, when you build a service, you need to consider the failure modes. Any system you build will fail. It's just a matter of when it will fail. So it really depends. So whenever the service grows, or if it doesn't grow, so you need to have an upfront knowledge of when the system will fail, and what are the types of failures that you can have, so that you can sometimes take proactive decisions to avoid that. Sometimes you can't always be proactive, so you need to have some reactive monitoring or reactive actions. We have these self-healing systems in Google that things go wrong and they heal themselves eventually. So these are the things that you need to consider, right? Now, first of all, component failures. That's you can't assume that a server or like a hardware or a compute, a CPU will never fail, or a RAM will never fail, or a network switch will never fail. So these are things that will happen. Again, some hardwares are more reliable than the others. We generally at Google, I think we try to prefer less reliable hardware. We don't go for the most expensive, very reliable CPUs or very reliable hard drives. We actually go for the cheaper, less reliable ones, because we know that we have already taken into account the failure modes, and our software will handle the reliability part. So we can have CPUs that have a short lifespan, but our software will take care of that. So that's where you need to make sure that you handle properly. Another important thing is query of death. What is query of death? Has anyone heard this term before? So query of death is it's a fancy name for a bad request. Whenever a user comes in, a bad request, a user tries to upload a photo that is 10 gigabytes. How will your system handle that? And trust me, if you build a service, somebody will try to do it, for sure. So you better have things prepared for that. Or you can also have like lots of requests coming in. We were going to DDoS attack, but you can have lots of bad requests coming in, a lot of 404s, or users trying to get an image that is very big. Somebody managed to upload a 10 gigabyte photo, and now they're trying to get that photo 100 times a second, right? So that again, that's where you need to take some action. So this can be a deliberate attack, or sometimes it's just bad luck.
you how we can replicate the services and we can have multiple instances. Now, query of death can actually destroy all the instances. The first request goes to the first instance, bad request, the instance dies. Then the load balancer forwards that request to another one. Then there's another one, and eventually you start killing all of your stack. So you need to actually think about it. You need to do some testing. We need to make sure that we properly validate all the requests before taking it down the stack. So maybe at the load balancer level or at the application logic, very early, we try to make sure that we have a good idea of what's going to happen, or if the inputs are valid or not. The next one is global rollouts. So avoid any global change when you're thinking of that. When you think of very highly reliable system, no matter how you have tested your change, things can go wrong, and you want to make sure that you're able to roll out things slowly. Test it in one location first, like test it in Europe first, for example. Make sure, let it soak for a week or so. Let's see how things pan out, and then eventually start rolling out to other regions. This is again one of the most common types of failures I've seen. Okay, we realize once we have rolled out to like 80% of our instances, we realize, oh, this was a bad release, and things start failing, and we roll back. So we do have automated rollback mechanisms as well, but again, avoiding global. No matter how sure you are that with the configuration or with the code, don't, unless it's an emergency situation. So have this in your processes when you roll out any change. And again, even the administrative commands, for example, you wanna just restart all instances, right? You're not rolling out a change. It's just an administrative action you're taking on your servers, on your instances. These things, again, even these things should be slowly rolled out because there are unexpected situations you can come with one global rollout. Yeah, so these are the 3 or 4 different scenarios that we have seen in highly reliable and scalable environments. I think, yeah, so if you want to know more about it, these are the books that I definitely recommend. If you want to build more scalable, reliable systems, this is where a lot of things I learned as well, or we learned. A lot of information, this is actually public, so I'm not spilling out any Google secrets here, really. So these are things you can learn without, even when you're not working on these systems. If you eventually want to work on these systems, this is where you start. That's it from my side.